Now, in this video, let us have the basic idea of artificial radioactivity. As we understand that if we have a nucleus, we can disturb this nucleus using a probe, and this nucleus can disintegrate using a probe. And the very first question arises is, what is artificial radioactivity? And it is basically a process by which a stable nucleus that we have, they are made unstable. So when you have this stable nucleus, we convert it into unstable nucleus. So this is a stable nucleus. By bombarding them with some high energy particles. And then these unstable nucleuses, what happen is that they decay, and they decay and give us nuclear radiations. And this kind of radioactivity is called as artificial radioactivity, where we instigate the instability in the nucleus, which is already in a stable state, by just bombarding it by an external particle. Now, these artificially made unstable nuclei, we call them as radioisotopes. We call them radioisotopes. And this artificial or induced radioactivity, it was discovered by Curie family. Now, let us take an example of what's called as let's take an let's have an alpha particle, right? And bombard this alpha particle. Suppose this is an alpha particle, and this is aluminum. This is the aluminum atom. And what happens is that we have this alpha particle, which is a product of some already existing unstable nucleus, say polonium. And what we have, the bombarded the bombarded aluminum with alpha particle, which is basically emitted by polonium, and the observed neutrons, and positron and proton coming from that aluminum. So what was the experiment was that you have aluminum, and we are bombarding this aluminum foil with alpha particles. And what they observed using a detector, is receiving that they were receiving some kind of penetration radiation, even after the polonium source was taken away. And the bombardment of aluminum with alpha particles was stopped, and after stopping this, they could further detect the penetration rays. And what were these penetrating rays? They were found to be positrons coming from this aluminum foil. So it's okay, you have alpha particles and you have the particles coming out of this aluminum foil, and you are detecting these particles. But once you stop, once you take off this source of alpha particles, you are still able to detect some particles, and these particles which are coming out of this aluminum sheet, they happen to be positrons in their original experiment. So this process can be given as, we have aluminum 27 and 13, and what we do, we hit it with an alpha particle, and what we achieve is P30. Let me put a star here, and 15. Now this P30 and star and plus what we obtain is a neutron. Now this P30 star is unstable. It's a radioisotope, and it decays to become it decays to become silicon, stable silicon. It decays to become stable silicon with the emission of a positron. In addition to this, we have positron and a neutrino. So, so the reaction proceeds. You have instigated a reaction like this, and this reaction proceeds, and what we have is we have P30 star excited state of P, and what we get out of it is silicon 30 and 14. And what in addition to this, we have positrons and we have neutrinos. Now, the radioisotopes, this is practically another element. Actually, what's happening that you have a transformation. You have phosphorus in excited state, and it turns out to be silicon. So, so this way, what we have achieved is that we could generate these isotopes by artificially bombarding this nucleus with an alpha particle. And now we have other examples in which we make use of neutron as a projectile. And using neutron as a projectile is a very good instigation of making a nucleus unstable, because it doesn't have a charge, and it can interact with the nucleus into the deep levels, and can unstable the nucleus. Now let's have some reactions where we make use of neutron as a projectile. Copper 65 and 29, we hit it with a neutron, and what we get is copper 66, that too in excited state 29, and what we achieve is a gamma ray photon, right? So this is unstable. So this is unstable, and it becomes stable by emitting a gamma ray photon. So what happens here? How to come up with this is that this copper 66 is a radioactive isotope, and it decays by emitting an electron. So it decays Cu 66 29. What happens? It decays and converts into zinc nucleus 66 and 30. And in addition to that, we have an electron and we have an antineutrino. So to say, what we have here is the zinc. Zinc is the end product of this reaction, hitting copper and generating artificially zinc 6630. And we can have more examples. Let me take another example of in which this neutron is used as a projectile. Take the case of this phosphorus 31 and 15 atomic number, hit it with a neutron, and what we have is aluminum 28 in excited state with 13 atomic number, and what we get out of it is an alpha particle. We get an alpha particle out of it, and this aluminum that we have, it is unstable. It is in excited state. It's a radioisotope now, and it decays by emitting an electron. So what it turns into is silicon 28 and 14, and it gives us an electron, beta particle, and an antineutrino. So this is another example where we are developing the radioisotope by hitting phosphorus with a neutron, And we can take another example as that of aluminum. We have aluminum 27 and 13, and we hit it with a neutron. It turns into sodium 24 star 11, plus it gives alpha particle. And this Na 24 and 11, this is unstable. And and what happens is that this sodium 24 11, this is the radioisotope, and what it does is it decays into magnesium. Decays into magnesium 24 and 12, and and gives out an electron, a negative beta particle, and an antineutrino. So these isotopes that we have here, that can be generated by instigating the nucleus of their parent nucleuses. They are of great utility for mankind, and so they are produced in very large quantities in atomic or nuclear bombs. In atomic and nuclear reactors.